And the last but not the least, Euclid's algorithm. Actually, Euclid's algorithm, we haven't yet completely discussed it, just mentioned it. So fundamental of theorem of arithmetic says things like any number, if it's natural or integer, can be factorized into prime factors, product of prime factors raised to some powers. On the other hand, division algorithm states you can uniquely find a quotient and a remainder for all naturals in uh, not n for all natural number a and b such that a equals bq plus r, and this r follows this in strict inequality or partially strict inequality, I should say. Yeah, this gets completely strict if we know that b doesn't divide a. If b doesn't divide a, then the remainder is always non-zero. So we get a strict inequality on both upper and lower bounds for r. That was division algorithm. And Euclid's algorithm. Okay, so let's
Sir, I have some doubts.
yeah, please.
I have done few sums from Barton. I have problem 2.2, page number 19, question number 1.
Are you talking about which book?
Barton, number 3.
Okay, Barton. So page number 19, problem 2.2, right?
Yes, sir, number 1.
Prove that if a and b are integers with b greater than 0, there exists a unique integer q and r satisfying equals to qb plus r, where 2b is less than or equals to r less than 3b. Okay, so it's not division algorithm. They haven't imposed any restriction on R. Like it's a different restriction. Yeah. So did you try to solve it?
Yes, sir, I have done a bit, but the answer is not much.
So can you explain what you tried to do and where you got stuck? So this is MD Burton, page 19, problem 1. So this says the question. So you have AB two natural numbers, or here two integers, as in case of division algorithm, and uh, so B is strictly positive. We have to so show that show that there exists unique Q and R such that A equals to QB plus R, The condition or the restriction on R here is instead of being in the interval 0 to b, it's in the interval 2b to 3b. Right. So what do we know from division algorithm?
A
Yes,
equals to
Sunny?
qt plus r.
Yeah, and that's just part of it. And what is the restriction on R we know? We know so from the solution. Rick Pal, someone wants to join. So Rick, is that what your name? You are new, right? You didn't join last class, right?
Yes, sir. Yes, sir.
Okay, so which school and which standard you are from?
Sir, I am from class 12.
Which school?
Sir, school is actually in Durgapur International School.
Okay. So you are also totally new here in RSM, right? It's your first class, right? Or you are like,
Exactly, sir.
okay. Okay. So, Rick, actually, last class, have you joined the classroom and got the notes that I like for the previous class and all that?
No, actually, there was a class. Actually, I didn't know that, so I don't have such kind of notes or whatever.
Okay. Okay. Till now, we have discussed division algorithm and fundamental theorem of arithmetic. You can have a look into the book of excursion in mathematics or any of the three books that I have suggested. I will repost. I guess the link for joining the Google Classroom is in the description of that WhatsApp group. So do join that link, and I will
Okay,
repost that. Yeah, that video and this notes along with it. Okay. Try to follow along. If you can't understand anything, you can message me privately later. Okay.
okay,
Okay. So yeah. So from division algorithm, we have for we if we have two numbers AB which are integers, then we know there exist unique integers q and r such that a equals to qb plus r, where 0 is less than or equals to r less than. There's actually a mod. Have they said anything about r being positive? Nothing as such. Okay. So this is what division algorithm gives us. Now in this equation, let me call this star 1 just a second. So if we add and subtract b, 2b here, like q times b plus r minus 2b plus 2b, this gives q minus 2 times b plus r plus 2b. Let's assume this is q bar. So q bar b, and let's assume this is r bar, so plus r bar. So previously we had the inequality 0 less than or equals to r less than b. Now we have if we add 2b everywhere, we get 2b less than or equals to r plus 2b less than or equals to b plus 2b.
Sir, sir, I'm
Yeah,
having some technical issues, so I'm joining from another account.
yeah, it's completely fine. Okay, so some of you are having trouble hearing me. Is that so? Yeah, yeah, Rick. I started with number theory since last class. Sorry for not looking at the chat. Okay, so Yeah, so 2b is less than or equals to r dash, less than or equal, so not less than or equal. Someone wants to join. Strictly less than 3b. So that's how we get two unique integers, namely qb and q dash and r dash, where r dash satisfies the proposed inequality between 2b and 3b. Is that clear, Koshan?
Sir, I have done in a different way.
Okay. So what's your way?
So, so at first I take another unique integer q dash b plus r dash, which I have assumed that these two are equal, like q dash b plus r dash equal to qb plus r, and then I have done my calculation and got b in bracket q dash minus q r minus r dash, and then I have put it in that expression to be less than equal to r less than 3, and then I didn't get the answer.
Oh, so you started with the equation that they gave and tried to show it implies the division algorithm like that.
Yes, sir.
So what was the issue that you faced?
Sir, at
Basically,
the end, it was coming to less than equal to q dash minus q less than 3. And how to prove it then?
you mean like this?
Yes, sir.
How did you get this inequality? Like, why are you putting inequality on Q? Like, we
I
only
have
need to
replaced the
get.
value. R
Uh,
minus R dash is equal to B Q dash minus Q. So I have replaced it the value.
okay,
So
okay,
I
okay. Starting with this equation, you started with this equation, right?
yes, sir.
So what is Q dash and R dash and Q and R like? Where did they come from all? Like here, my
They are all
equation,
integers, and I have assumed that they are equal.
you mean Q dash B plus R dash is equal to QB plus R, right?
Yes, sir.
And B is equal to B. So this equation actually means implies Q is equals to Q dash and R is equals to R dash. So like this is just
Sir, I just thought to do it in a contradiction process. Like our assumption is wrong. That means that they two are unique integers. They two are not equal.
okay. Okay, okay. Sorry. So you have the restrictions different, right? Here you have R dash less than 3b and greater than equals to 2b, while here you have 0 less than R less than b. And you assume they are equal to a. There is that unique thing. I don't think you can bring about. You can like later prove it's unique R and R dash with this kind of logic. Even if you prove that there is a contradiction, even if you find a contradiction, what will that imply?
That they are not equal. They are unique.
Uh, I'm not getting actually why proving it they are not equal will prove this. Can you later send me your solution? I will try to have a look and then.
Okay, sir.
Okay. So
Okay, sir.
yeah. So now for now, let's skip this problem. I mean, this is a way to solve this, like assuming division algorithm, which is always true. and then building on top of that to come up with that inequality which is here, which is given here. But since that uniqueness, inheriting that uniqueness from division algorithm, I don't need to prove that q dash and r dash are unique. It follows from q and r are unique. So q dash and r dash are the required integers. Okay, so Euclid's algorithm, yeah. Before we talk about Euclid's algorithm, I wanted to talk about induction and well ordering principle. These are proving techniques which are very essential for in number theory, in geometry, in combinatorics, or in any field of mathematics. It's just a very basic proving tool. So induction. So anyone of you have any idea what induction is? I'm sure you must have heard it. Like whenever you read a proof, they assume that there is a base case which is true, and whenever n is true, then n plus 1 is true. And like how they prove, first they claim something and then they try to prove it. Okay, so suppose you want to prove the formula for the sum of the first and natural numbers. So 1 plus 2 plus 3 plus 4 up till n. What is this? So up till n is equal to n times n plus 1 by 2. Similarly, you have 1 squared plus 2 squared, 3 squared, up till n squared equals n into n plus 1 into 2n plus 1 by 6. Right. So how do you prove any one of these formula? First one is easy. Typically, we revert. First, we introduce a new variable s for the sum, and then we write s in a different way, n plus n minus 1 plus up till 1. And then we add these two equations, getting 2s on the left side, and each of the terms become equal to n plus 1, which helps us to add them up as n times n plus 1, since there are n terms in total. And then dividing it by 2, we get s. So s is n into n plus 1 by 2. That was easy, but what about the second one? If you do the same way and revert s, then you will get n squared and above that 1, so you get n squared plus 1, and then n minus 1 squared and then 2, n minus 1 squared plus 2. Then you are stuck, since n squared plus 1 isn't equal to n minus 1 squared plus 2. So the same kind of technique doesn't work here. So what do? You can always check for yourself whether or not this formula is correct by just observing patterns. Here you can put n equals to 2, 3, or anything, and then check whether that's equal to 1 square plus 2 square up to n squared. After you have done it a couple of times and you are pretty sure that it's the correct formula, observe that this formula is of degree 3, so you just need to check it at 3 distinct values of n. That should make it pretty tight. So now you are pretty sure about a formula for some sequence or anything, and now you want to show it that that is the formula. So these are the situations where you will like to use induction. So induction says if you have Imagine this is like a queue of dominoes or a stack of dominoes. I'm pretty bad at drawing dominoes. I imagine they are something like that. So this is a line of dominoes. You push the first one. So this is the zeroth domino. This is the first domino. This is the second domino. This is the third domino up till. Suppose this goes up till infinity. You push the first domino. It topples. Pushes the second one. It topples, and it pushes the third, and the whole thing continues. It's a domino effect. So if you see that these dominoes, they have indices more or less in the set of natural numbers, right? So that's what induction is. If there is a statement P which you can index by some natural number n, so n is a natural number here, and if you want to check the truth of that statement P, you want to check whether statement P holds for all natural numbers, and you can try out locally whether it holds for, say, suppose k, for k equals to 1 or 2, or if p1 holds. If you know, you can check that manually. If p5 holds, then, and you can also say things like, if pk holds, then I can say pk plus 1 holds. Then you can say pn like pn holds for all natural numbers. That's because if like, what is true for the system of falling dominoes? You have given a push at the first domino, so there is a domino which is falling, like p0 holds, or the first domino is getting pushed and is falling. And for any domino, any other, like for all dominoes, if it falls, the next one also falls, or you have to ensure that there are no spaces between the dominoes, so that this process continues for up till infinity. Okay, so formally, there are two formulations of induction. One is called principle of finite induction, and the other one, principle of complete induction. Finite induction is the simpler one of the two. It says if you have a subset S of natural numbers, that is the set on which you know you want to show is equal to n, right? So you have set S of natural numbers, and the following are true. So the following are true. Number one, 1 is inside S, right? And number two, n is inside S implies n plus 1 is inside S for all n uh, for all n in S. Okay. If these two statements are true, then we can say S is equal to n. That is the set of natural number n. Okay, so you see, n is an infinite set, right? It is infinitely many elements, and so can be S, or it can be finite. We don't know. Okay, so how do we say? How do you know if a set is finite, A and B? Then we can talk about their lengths. So A can be, if A's number of elements is smaller than B, then A is smaller than B, and vice versa, right? If they are equal, then all the elements are same. So what about infinite sets? How do you bring about a notion of inequality in their sizes? They are both infinite, right? So that doesn't make sense. Which one of them is larger and which one of them is smaller? So that's where all these counting principles come into effect. Like everything that is, just remember everything that has a numbering. So you can, if you can number them, then it's probably the same size as natural numbers. So say suppose what can you say? Mm, yeah, like these dominoes. So you can call that the first domino, the second domino, the third domino, and all that. So you see, in this way, in this numbering, we have all the dominoes mapped to some number in the set of naturals. One, two, three are all natural numbers, and none of the dominoes are left out. And yeah, in this way, you can show that each natural number k will get a domino, and each domino will get a natural number. That's why the set of natural numbers is equal to the number of dominoes on this infinite line of dominoes. So there we say there is a bijection between the set S and the set of naturals. So so S equals to N means there exists a bijection between S and N. So that's the simpler one, the principle of finite induction. The principle of complete induction, or also sometimes known as the principle induction strong form. This also has the same assumptions on S. S is a subset of natural numbers. We want to check whether or not S is equal to N. We have the following things true. So given 1 is inside S, and instead of assuming N inside S implies N plus 1 is inside S, we have a much stronger assumption. So 1, 2, 3 up till N. This whole thing is a subset of S. Then that implies N is inside S. Sorry, N plus 1 is inside S for all N in S. So if 1 and 2 hold, we can say S is equal to N. You can easily prove the first principle of induction from the second and the second from the first. So these two definitions, these two formulas of induction are essentially equivalent. Just in some problems, you will find it easier to apply the second form and another form. And other times, you will find it easier to apply the first one. Sorry, actually, this is inferable, but still, it's n plus 1. This whole thing is a subset of S. So using that, can you prove this formula? Uh, Anyone wants to try?
Yes.
Yeah, so I will give you like 5 minutes to try it out for yourself. Okay.
So can you please show me the question?
Yeah, so you have to prove the sum of the square of the first n natural numbers is equal to n into n plus 1 into 2n plus 1 by 6. Okay, so 5 minutes are kind of over. Who wants to tell me the solution? Let me ask one of you. Shonok, can you
Sir,
unmute?
I am doing.
Yeah, you try, but I will ask one of you, but like just to see if every one of you is like joined and following the class. Shonok,
Yes,
can you
sir.
hear me? Yeah, so did you try to prove this one?
Yes, I tried, sir.
So, like, so could you prove it, or you got stuck somewhere?
Sir, I did, sir, for 1 square plus 2 square, sir, it is working. So, sir, like, I'm taking it
Yes.
as P1 and then, so,
Mm-hmm.
sir, like, after that for Pn, it will work. And similarly for P of n plus 1, if it works, then it is proven,
Yeah. So
sir.
did you check it if for Pn plus one it's working or not? Assuming it works for Pn.
Sir, there I'm getting a little stuck, but I think, like, if I put it directly, then it will. I haven't, like, done that part only, like, sir, of P of n plus 1, that is only left.
Okay. So that is the main part, the inductive step. So let me write the proof formally. I will just do it once, and then for the rest of the problems, I will just write the inductive steps. So the question is, show that sum over k squared, k runs from 1 through n, equals n plus 1 times 2n plus 1 by 6. So proof by induction. So we first define our induction statement. So Pn says k equals 1 through n, sum over k squared equals n into n plus 1 to n plus 1 by 6. We want to show Pn holds for all n naturals. That is, P1 is true, P2 is true, up till P infinity is true. So first we have to check the base cases. So base case. Base case is just P1 here in this case, since uh, yeah, so it is P1. So P1, the statement P1 is 1 square equals to 1 into 2 times 3 by 6. It's simply 1. And this is LHS. Sorry, actually, you should write it as LHS equals 1 squared, and RHS equals 1 times 2 times 3 by 6 equals 1. Therefore, LHS equals RHS, and we are done. Okay, so this QED is a French acronym or something which basically means proved. You can look up the internet to find its full form. So that's done for base case. Now, the induction hypothesis. Induction hypothesis. So we're using the finite form, or this weaker form. So we will just assume it holds up to Q. Anyone writing in the chat or something? Okay, okay, yeah. So who is this? Rick. So Rick found out this QED stands for quad eret demonstrandum. Okay, whatever. So Rick, can you explain what each of these words mean specifically if you have looked? Yeah, Rick. Hello. Okay, I don't know why Rick left the meeting. I hope he rejoins soon. So induction hypothesis, we assume PK.
Can you hear me?
Yeah, yeah, I can hear you.
Yes,
Rick.
yeah, there was a mic issue, so that's why I couldn't talk. So actually, I got about this keyword QED is actually means that whatever I wanted to justify the statement is got. I mean, we have got the statement actually we wanted to. So that's the meaning of this word QED.
Oh, okay. And these are French words, right? So,
Yeah, actually French, but as far I knew that this word is actually Italian words. Uh, was
oh, okay.
used in past in like mathematicians used to use this word in their proofs in their papers. So I guess this is it an Italian word.
Okay, thank you, Rick. So this basically stands
Welcome.
for proved. So let me write in quotes. Okay. So assume Pn is true. Pn is true to show Pn plus 1 is also true. So here you will write down Pn. That's your assumption. So you have sum over k squared. K runs from 1 through n plus 1 times 2n plus 1 by 6. Okay, so that's is true, right? That is from our assumption. Now you add n plus 1 both sides. n plus 1 square at both sides. That's obvious since you want to make the left hand side equal to k runs from 1 n square k square, right? On right hand side you get some formula which you will simplify and try to write it down in the form that you need. So left hand side is set. You have
Yes,
got
sir.
what
This
we
was
wanted.
what I was getting, but I could not
Yeah,
transform
yeah.
it into that formula.
Okay, just you take LCM and then break everything up. You will get that formula if it's anywhere true. So it's 6 times n plus 1 squared. You take common n plus 1. You get n to n plus 1 plus 6 times n plus 1 by 6. I guess we have to multiply them. 2n square plus n plus 6n plus 6. Now we need a n plus 2 term, right? Hmm. Mm, uh, Basically, what you will do, you can take a rough sheet down and then, so this is my rough sheet. And you write down the thing that you want. You want it to be n plus 1 times n plus 2 times twice n plus 1 plus 1 by 6. Just forget about the denominator since it's already 6. So you want this thing to be 2n square plus n plus 6 n plus 6. You want that to be n plus 2 into n plus 1 plus 2. So let's simplify the top one. We have n plus 2 and leaving out n plus 1 since we have already got that. 2n plus 2 plus 1, 2n plus 3, 2n squared plus 4n plus 3n plus 6. So it's 2n squared plus 5n, 7n plus 6. So now you can write those steps in reverse now in here. So you can make 2n squared plus 4n plus 3n plus 6. It was basically a middle term factorization. You could have done it anyways. It's still, many a times it's not that simple. So take common 2n, n plus 2. Take common 3, n plus 2. And we get n plus 1 times n plus 2 times 2n plus 3. You add one last step, taking common, taking 1 inside the bracket, plus 1 by 6. So rough page ended here. And so sum of the first n plus 1 naturals is equal to this. And then you identify that this is Pn plus 1. So you assumed Pn is true, and then after a few algebraic steps, you got Pn plus 1. So that is true. So you could have written is true all along the way. Okay. So Pn plus 1 is true. That is Pn implies Pn plus 1 is true. And you didn't had any assumptions on n. So this holds for all n naturals. So by the principle of mathematical induction, Pn is true for all n naturals. Right. And the definition I have used the language of a set S. So you can use n here directly, or if you want to use S, then you have to define S explicitly as all those n such that Pn is true. And after proving it, you got S equals to n. Okay, so that's it for induction. You can try out several exercises. So I will give you a few exercises for home task. You can try out the cube one. So prove that. Show the following. Using induction. You can use any one of the two forms, either the strong one or the weaker one, the finite induction. So 1 cube plus 2 cube, 3 cube up till n cube. This is, as far as I remember, should be n into n plus 1 by 2 whole squared. Am I right? Does anyone remember or recall this formula? Let me check.
Yes, sir.
Yeah.
Yes, sir. The formula is there only.
Okay, so yeah, so n was 2, sorry. So it's 9. Here it's coming 8 plus 1, 9, yeah. So it's more or less true. Second one, just a minute. So there's something called triangular numbers. So they look like these. The first one is a single dot. The second one are three dots in the form of a triangle. And the fourth one is mm, yeah, and so on. So if you write the number of uh, numbers in each of the dots, sorry, the number of dots in each of the triangle, you get a pattern. So it's 1, then 3, then 1, 2, 3, 4, 5, 6, and the next one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So this is a sequence. This is a sequence of triangular numbers. So we call the first number T1 and the second one T2, the third one T3, and so on. The kth number Tk. So that's how we write this sequence in a compact notation. This Tn enclosed by two braces, two curly brackets, with a suffix of n greater than or equal to 1 to signify the starting index of 1. We're starting from T1. Some might prefer to start from T0, then they write n greater than or equal to 0. This is standard notation for sequence. So here you have to show T1 plus T2 plus T3 up to Tn is equal to n into n plus 1 into n plus 2 by 6. Okay, so triangular numbers. Third one, just a minute. Try to show 2 power n is less than n factorial. So that is the statement Pn. This is inequality. So n here is greater than or equal to 4. Obviously, the first three statements don't hold. So 2 power 1 is uh, 2 power 1 is greater than 1 factorial, which is 1. 2 power 2 is similarly greater than 2 factorial, which is 2. 2 power 3 is also greater than 3 factorial, that is 6. But from 4 onwards, 2 power 4, that is 16, is less than 4 factorial, that is 24. Uh, I hope every one of you are familiar with this factorial notation, right? So n factorial, or some might write it as this notation, this angle notation, is spelled as n factorial. So it's the product of the first n numbers, n natural numbers. So 1 into 2 into 3 up till n. So we have to show 2 power n is less than n factorial for all n greater than or equal to 4. So solve them for you as an assignment, or yeah, you can discuss it in the next class if you can't. So let's now move on to well ordering principle. Uh, so any one of you familiar with this principle, or I heard it
Yes, sir.
anywhere? Yeah, Yeah, who is speaking?
Sir, Shaunak, sir.
Yeah, Shonok. Continue. So you have
Sir,
heard
like
about
in a
well-ordered
set,
principle. Hmm.
sir, in a set, there has to be a like an element which would be the smallest among all the other elements. So I think that is the well ordering principle.
Okay, so what are the assumption on that set?
All the
Are
elements
you
belong to real numbers,
not real, natural numbers?
natural numbers. Sorry.
Yeah, and there is additional one assumption that S can't be no empty set, right?
Yes, sir. Yes. Yes.
Yeah. So as Shonok said, so we have two assumptions. So first, S is a subset of natural numbers given uh, S is non-empty. So S is not equals to an empty set. And yeah, the first assumption is already met. That's S is a subset of N. Just let me see if they have any more assumptions. No, nothing much. Cool. So this, then we can say S has a least element or minimal element. You can call it small s or anything. Okay. So why does this obvious thing so important? It turns out that the principle of mathematical induction and this well ordering principle both are equivalent also. So you have a equivalence relation. Sorry, equivalence what can I say? String of equivalence, right? So we know the following are equivalent. Number one, principle of finite induction, also called PFI. Number two, principle of complete finite induction, also called PCI. And number three, the well ordering principle, also called WOP. So what does it mean for them to be equivalent? Well, so if you have a set S, which is subset of naturals, so like if yeah, so if S, since this is common in all three of them, so if S is a subset of natural and they satisfy the conditions of PFI, then that implies they satisfy the condition of PCI, which in turn implies they satisfy the condition of WOP. And similarly, WOP also implies PFI. Like all the 3C2 permutations of implications are true. Actually, 3C, not 3C2, it's actually 3P2. So 3P2. equals to twice of 3C2. That is PFI implies PCI, PFI is implied by PCI, then WOP implies PFI, and then the other way around, and all of them. These all are true. So how do you prove such equivalence relations? Uh, like there are many ways to do it. You can start from any one of the three statements. Like if you want to show k statements are equivalent, they are listed as 1, 2, then up till k. Then you show p1 implies, I mean the first statement implies the second one. Then you prove the second implies the third one. Then you prove the third implies the fourth one up till the kth one, and then you prove the kth one implies the last one. Sorry, the first one, and then you don't need to show any of them, any other equivalence. Sorry, any other implication. That is, you just uh, prove n implications explicitly. So just prove n implications explicitly. These are actually not one-way implications, these are both-way implications. So you have to show 1 happens if and only if 2 happens, and 2 happens if and only if 3 happens, and all that. So you just saved yourself a lot of work. Instead of NC too many implications, you just showed n of them. So you saved yourself quadratic amount of work. Right. So then you can, like, you don't need to prove it, but everyone knows that if you want to show, say, suppose the ith implication and the jth implications are equivalent, then since you have this implication ready, this implication sequence ready, you can just concatenate those proofs and say I implies I plus 1 is true, it implies I plus 2 is true up till j plus 1, j up till j is true. You can like add those j minus I minus 1 proofs. That should be enough to show I and j are equivalent. Okay, so here we only need to show 3 proofs. PFI implies CFI, implies PCI, and PCI implies WOP, and WOP implies PFI. The order doesn't matter here. You can permute them in the way you feel the proofs are easier to do. Okay, so should I discuss the proofs now, or they're not actually that much relevant? But still, if you okay, so let's prove few of the implications. So let's show yeah, PFI and WOP are equivalent. Let's do this implication. So what have we assumed? So first assumption is PFI is true. So S is a subset of natural numbers, and from PFI we have uh, 1 is inside S, number 2 is n inside S implies n plus 1 is inside S. all n. And this thing implies uh, this whole thing actually, s is equals to n. So we know that. So we know this. This is our assumption. Now let's try to prove WOP. So what does WOP says? So WOP says we have a subset S of natural numbers, and we want to show uh, so S is non-empty. This is our assumption. So to show S has a least element. So how to show S has a least element? So we can define a new set T. So T is just n without S. So all the elements that are not inside T but in natural numbers are not inside S but in natural numbers are inside T. Okay, so now we know the set of natural numbers has a least element, right? That is 1. So n has a least element, namely 1. So let's condition upon that. So if 1 is inside, let me make a small flowchart. First, we have 1 is inside S. Now observe that S is a subset of n, and so the least element of S can't be lesser than the least element of n. So if 1, which is the least element of n, is already in S, all other elements of S have to be strictly greater than 1, right? Therefore, for all, like, since for all n in n, 1 is less than or equal to n, and S is a subset of n, this implies for all s, small s in capital S, we have 1 is less than or equal to S, since S in n, n since n is the superset of S. Right, so we have got the least element of S, that is 1, right? So 1 is the least element. So 1 is the least element. So S has a least element. And then we are done. So that was the easy part. Let's see if 1 is not inside S. So that implies 1 is inside T. Right. So 1 is inside T. Now, so now how can we show I guess you have to use an Archimedean property, which I haven't yet discussed. Just a minute. Yeah, we can prove it likewise as we can apply induction on T. Observe that S is a subset of N, so that implies N minus S is a subset of, that is, T is also a subset of N. Right, so we can apply induction on T. So applying induction on T. Since induction is our assumption, we have assumed PFI. So we know one is inside T, we just showed. And number two is we can assume K to be, or N to be inside T. Sorry, N to be inside T. So what does that mean? So that means N is not inside S. Uh, N is not inside S, and we have to show N plus 1 is inside T, or N plus 1 is also not inside S. So what would have happened if N plus 1? Okay, so let's just bifurcate again. So basically, like you can take the set S, divide it, then you make a decision tree like this. This is one is inside S. This is one not inside S. If one is inside S, then we are done. One is the least element. If one is not inside S, we bifurcate it once more. Accordingly, if two is inside S or not. If 2 is inside S, then we are again done. Since 1 is not inside S, 2 is the least element, and then further on. So you get it, so in the kth step or the nth step, we either have n inside S or n not inside. If n is not inside S, then we have n plus 1 inside S or n plus 1 not inside S. So if n plus 1 is inside S, then we are done, since n plus 1 is the least element, since all the numbers from 1 up till n are not in S. And if n plus 1 is not inside S, then n plus 1 is inside T. So we were applying induction on T, right? So we just showed n plus 1 is inside T. So by principle of mathematical induction, we have t is equal to n. So we can show t is actually same as n, and that will imply s is equal to n without t, that is n without itself, that is a null set. Anything without itself is a null set. So that is a contradiction to our assumption that S can't be a null set. So this is a contradiction to our assumption that this thing can happen, that n plus 1 is not inside S. Actually, to make it a proof by contradiction, we would have first assumed that S is not here. So assumption for this sake of contradiction, S has no least element. And then this contradiction would have linked to this assumption. So we would have proved our contradiction and uh, proved our assumption wrong. So S has a least element. But I tried to uh, structure the proof in a different way, in a more intuitive way, where we don't start with assumptions and contradiction, but we first try to see why it is true. Okay, so everyone got the proof or the idea of the proof, like how you can show well ordering principle from induction, not the other way around. I haven't proved the other way around yet. So this is basically the proof why well ordering principle is implied by induction. Uh, Try to prove the other way around as your homework. Show that WOP implies the principle of induction, the weaker one, I mean. Okay. Okay. So doubts, anyone about this proof?
Hello, sir.
Yeah. Yeah, Rick.
Yeah, yeah. Actually, just in the last proof, I wanna ask that there is a list element in the S. That's the our agenda to. That's the topic. I mean, the line we have to prove. But how could I prove that there is a list element? Actually, we have proved that one not belongs to S, and then whatever we have done, and that's all true. I completely agree. But where is the shortest? I mean, least element that we have proved there?
No, we don't explicitly need the least element. We just uh, prove its existence. So I have structured this proof a bit
Oh,
awkwardly. So we have to assume initially the proof should start from the assumption that S has no least element. And then it will go on proving that then S can't contain 1, since then that will mean S has a least element. So then
oh,
this
okay.
branch will be crossed out, and then we can apply induction on T, and followingly we can say that if n is not inside T, so n is inside T, that is n not inside S, then n plus 1 also can't be inside S. And that's how we can go on to show T is actually the whole set of natural numbers, and then S becomes empty. Then we get a contradiction, and then we disprove the claim that S has least element. This proved the negation of the claim. Yeah, so we proved the claim.
Okay.
Okay.
Okay. Thank you.
So last day I talked about Bejout's theorem. I just mentioned the name, I guess. So let's try to prove that with well ordering principle. So we have uh, the GCD or the HCF or a GCF or anything. So GCD or HCF is basically the greatest common divisor or the highest common factor of A and B. That is the largest number which divides both of them. So Bejout's theorem says if A and B are integers, not natures, okay, integers, and both are not zero, so AB is not equal to zero. Not AB. A is greater than, how should I say it? A not equals to zero or B not equals to zero. So then there exist X and Y such that GCD of AB is equal to XA plus YB. These X or Y are not unique, so you get infinite many pairs of X and Y. Right. So yeah, so how to go on proving this? So we obviously using well ordering principle. So we want to use well ordering principle to prove this. Well ordering principle. So we can take S to be the set of all possible or the span of the elements of the form ax plus by. Since the GCD is a positive number, we can impose this additional condition of ax plus by being greater than 0. Since we want to make S to be a subset of n, and n don't contain negative numbers. So this is the set of all possible ax, all possible numbers of the form ax plus by. We want to prove that GCD of AB is also inside this set. So to show GCD of AB is inside S. So let's use well ordering principle. So by well ordering principle, we have a least element in S, call it G. So G be the least element of S. Sorry, first I needed to show S is a subset of natural number and S is non-empty. So why is S a subset of natural number? Can anyone of you point out? Uh, Prasenjit, yeah. Can you say why S is a subset of natural number?
Yes, sir.
Yeah.
Can you give me a minute?
A hint. Uh,
So,
like uh, natural numbers satisfy few properties of multiplication and addition, right? Like when you add two natural numbers, you get a natural number. When you multiply two natural number, you also get a natural number. So
Yes, sir. Yes.
natural number is closed under multiplication and addition. So that's
Yes, sir.
why all all of them are
Natural numbers. That's why S will also be a natural number.
yeah. So S is a subset of natural numbers. That's right. And why is S non-empty? Can you find one example, like one number which is already in S? You can put
So
X, yeah.
we can take any number and put ones. We can take one or any other number greater than zero inside S, so it will always be a non-empty set.
So you mean one is always in S? Like see the definition of S. It says all the numbers of the form ax and by, ax plus by, and we have not yet fixed a and b. So you have to give
So,
them in terms of a and b, obviously. You can see one number that is independent of a and b, and that is zero,
so
right?
but x plus by is greater than zero.
Yeah. That's why you zero is not in S. So you can take x equals to 1 and y equals to 0 instead and say A is inside S, so is B.
Yes.
Yeah, so obviously S is not empty. Okay, thank you, Pritesh. So, so that's why we can apply Wheel-Audrin principle and infer that G has a least, sorry, S has a least element G. So G is the least element, so G is of the form AX plus BY. Since G is a particular element, I'm subscripting these Y and X by G. So G is equals to G is equals to AXG plus BYG. Uh, now, now we will actually go on proving that this G is actually the GCD of A and B. So for that we need to first show G divides A and B. So G obviously divides, or, or let's take a factor. So let F be a factor of G. So F divides G. F is a natural number and F divides G. This implies F divides AXG plus BYG. Okay. Now suppose G doesn't divide A, assume. So now we can use the division algorithm. So assume G doesn't divide A, so by division algorithm, we have A equals to GQ plus R. So there exist unique Q and R inside naturals such that this happens, and the condition on R is strict on both sides, bounded by 0 and G. We don't need the uniqueness here, but this inequality is important now. So we get R equals to A minus GQ. Uh, so now, yeah, we can now replace that. We know G is equals to AXG plus BYG. So replacing that, we get AXG plus BYG. Taking A common, we get 1 minus XGQ plus, not plus, minus, minus BYGQ, right? So now observe that this thing, this 1 minus xgq, you can now take it as xr, and this ygq you can call it yr. So r is equals to axr plus, or you can take the minus 1 also along with the minus 1, plus byr. So this is exactly of the form that is mentioned in the definition of S. So that implies R is in S. Right. Now you look at the condition that division algorithm gave us inequality. So, but R is strictly less than G, and we assumed G to be the least element of X of S. So here we get a contradiction since we get a smaller element of the more smaller than the least element. So we naturally get a contradiction to our assumption. So which one of our assumption we get a contradiction to? Hmm. Yeah. Uh, just a minute. Where did I write it? Yeah, this assumption. We assume G doesn't divide A. So this contradiction is for that. Hence G divides A. So uh, yeah, and G divides A, and G is the yeah, not needed. So G divides A, and similarly we can show G divides B. That implies G divides the GCD of A and B. Right. Okay, but to say this is the GCD, we need to show that GCD itself divides G. Just a minute. So basically, from this equation, if yeah, from this equation, if GCD of A and B is anything else, suppose G dash, then the G dash divides right hand side, the G dash divides A, and G dash divides B. So G dash divides right hand side, and G dash also has to divide the left hand side, right? So that's why G is equal to the GCD of A and B, and that ends the proof. Okay, so is that more or less clear? So that was a pretty nice application of both well ordering principle and division algorithm all in the same proof. Okay, so let's end our discussion with Euclid's algorithm. We didn't complete it last week. It's Euclid's algo. So as I just demonstrated last week that uh, in your primary school you must have that division rule for finding HCF. Say suppose for between 12 and 18. So you first took the smaller one and tried to divide the larger one with it. So you got some remainder 6, and then tried to divide the divisor with that remainder. So you got 2, and keep on repeating it till you get a remainder 0, which fortunately you got in step 2 in this case. And then you mark the corresponding divisor as the HCF or GCD of the given two numbers. So GCD of 12 and 18 is 6. So basically if you are using division algorithm repeatedly, so first you have two numbers A and B, and suppose they have a GCD G. Suppose also A is strictly larger than B. So you write B is equal, or A is equals to BQ1 plus R1. R is in between uh, 0 and B, that is strictly less than B and strictly more than 0. And then you write B is equals to, sorry, R1. B is equals to R1 Q2 plus R2. Similarly, R2 is inside 0 and R1. Then R1, sorry, R1 is equals to R2Q3 plus R3. R3 is also inside 0 and R2, and like that until and unless you make the remainder, that is the Ri, 0. Suppose in the kth step you get Rk minus 1 equals to Rk minus sorry, Rk minus 2 equals to Rk minus 1 times Qk plus Rk, and Rk is 0 here. So this is basically just Rk minus 2 is equals to Rk minus 1 plus Qk. So then you say Rk minus 1 is the required GCD, is the GCD. So why is it true? So you can see if you can write Rk minus 2 in terms of Rk minus 1 with, like, Rk minus 1 divides Rk minus 2, right? And what was the previous equation? Here there was Rk minus 1, and now here there was Rk minus 2. So obviously this there was Rk minus 3. So Rk minus 1 divided both Rk minus 1, since it divides itself, and it also divides Rk minus 2 from the kth equation. So Rk minus 1 divides Rk minus 3, and that in turn implies r divides rk minus 1 divides the previous rk minus 4, and so on up till r divides b. I mean rk minus 1 divides b and rk minus 1 divides a. So rk minus 1 divides a and rk minus 1 divides b. And since any of the previous r's like r1 up till rk minus 2 didn't have this property, so rk minus 1 is the least, uh, not the least, the largest, or like these r's are all strictly in the descending order, right? So we have r1 bounded by 0 and b, then we have r2 bounded by r1 and 0, and r3 bounded by r2 and 0, and so on. So this implies rk is less than rk minus 1 less than rk minus 2 up till b less than a. All of them are like this. Rk is 0 unfortunately. So this is the string of inequalities. So all these larger Ri's were contenders of GCDs for A and B, but they unfortunately didn't divide A or B since they gave out remainders. But Rk minus 1 is the largest one which divides both A and B. So this is the GCD. So if you like substitute the value of rk minus 2 in the topic in the equation just before it, and then use that to substitute the value of rk minus 3 in the equation before it, and then continue, you will eventually get an equation of the form a equals to some um, you mean like bq1 plus rk minus 1 times some q1 dash. So you finally substituted the value of r1 with in terms of rk minus 1. And now if you rearrange, you get so I guess this equation won't look like. Okay, let me use a working example like for 12 and 18. So we have 18 equals to 12 times 1 plus 6, and we have 12 equals to 6 times 2 plus 0. So now we can replace 6 as, so we are replacing the value of 12, not 12. Yeah, 12, yeah. So we're replacing the value of 12 here above. Uh, Actually, in this case, it's too simple since you can just manipulate the first equation as 6 equals to 18 plus 12, 1. And since we know 6 is the GCD, I just wanted to point out how we can like find one pair of solution for the Béjou's equation using Euclid's algorithm. So if you were asked to find x and y such that ax plus by is equal to the GCD of xy, then you can carry out the the Euclid's algorithm, like find the system of k equations, and then go on back substituting until you reach the first equation, and then you get uh, an expression of the form ax plus by. So I have to find two numbers which have GCDs for them to last at least a few lines more. So, okay, so excursion as an example, let me use that. So 4840 and 1512. So we have 4840 equals 3 times 1512 plus 304, the first one, and then we have 1512. If we divide it by 304, we get 4. So 4 times 304 with a remainder of 296. Then we divide 304 with 296, we get 296 times 1 plus 8. Then we divide 296 by 8, we get 37 plus no remainders. Yeah. So now we substitute the value of 296 here in the top equation. We get 304 equals to 37 times 8 plus 8, and then we substitute 304 in this equation. We get 1512 equals to 4 times 304 is 38 times 8 plus 296. Then we substitute the value of uh, okay, we can actually directly substitute the value of 304 here in this equation. 4840 equals to um, 3 times 1512 plus 4 times 38. 38 into 4, that's 152 times 8. Yeah, so plus 296. And for 296, we have this equation. Substitute that. We get 4840 equals 3 times 1512 plus 152 times 8 plus 37 times 8 for 296. So we get 4840 minus 3 times 1512 equals 189 times 8. Uh, just a minute. If we divide it by 189, I guess substituted it wrongly. Okay, so sorry, instead of doing it this way, yes, instead of substituting from the bottoms up, we have to substitute 304 into here. So 304 is 4840. Uh, for convenience, I will write 4840 as A and 1512 as B. So 304 equals to A minus 3B. So then we get the second equation as 1512 is B. So B equals to 4 times A minus 3B plus 296. So that gives 296 as minus 4 times A and plus 4B, right? And then substitute it in here. So that gives 304 we already know is A minus 3B. 296 is uh, minus 4A plus 4B plus 8. 8 is already the GCD, so we can now write 8 as 5A 5A minus 7B, right? So that is just 5 times 4840 plus minus 7 times 1512. So x is 5 and y is minus 7. So we found the coefficient for Béjou's formula, right? So we express the GCD of A and B as a linear combination of their linear combination of them. Okay, so as your assignment, try this on two large numbers. So let me find two large numbers. So find x naught, y naught, uh, such that x naught, y naught are integers, of course, such that GCD of 1, 2, 3, 7, 8 and 3054 equals to x naught times 1, 2, 3, 7, 8 plus y naught times 3054 using Euclid's algorithm. So then try this out along with the first three problems that I gave. Where are those three? Yeah, these three induction exercises. And we will discuss them in the next week. So let's call it a day here. If you have any doubt, you can ask me in the next class. Okay. Thank you and good night.